Okay, thank you very much. So yeah, so what I'll be talking about today, the title was a bit of a mouthful, so thanks for saying it all. And I'll try to break it down now. So the main practical contribution of the paper is a machine-checked proof of $CPA, and so essentially secrecy and plaintext integrity security for some x86 assembly code implementing Mac, then encode, then CBC encrypt, so MECBC that's used in particular in the TLS record layer. And we're obtaining this proof against some timing adversary. So why look at MECBC? So it's simple crypto, so there's not that much difficulty in the top level of the proof. But it's actually very difficult to implement securely. It's one of those examples that went kaboom quite a number of times. Why do we want it to be machine checked? So the first thing is really, actually really necessary to machine check those proofs if we want to take all implementation details into account. So especially doing hand proofs on x86 code is not going to be something you want to do. And also it's necessary to verify implementations for properties that are not easily testable. And one such example is their timing behavior. And in particular for MECBC, that timing behavior has been exploited in the past to break it. And we show a new attack on the S2N implementation of MECBC. And to achieve this proof, and in order to make it feasible to obtain it, we actually also present a framework that breaks it down into simpler problems. So first considering black box security, then lowering that down to implementation, black box security, and then taking side channels into account. So I'll first start by presenting a brief overview of MECBC and of our attack, and then go into details about the proof process and the framework. So a quick overview of MECBC. So it's an authenticated encryption scheme where you have a payload, the plaintext, that is fed through the MAC with some additional data. The payload and the MAC tag are concatenated and padded to a multiple of the block length for the block cipher. And then the result is fed through AES-CBC in CBC, yeah, AES in CBC mode. So it's MAC then encrypt, which is not ideal. And it's not ideal in particular because when decrypting, you need to know the length of the padding before you check the MAC. You need to check the validity of the padding, but you need to do all this without revealing anything about the decrypted ciphertext until you've actually checked the MAC, because the decrypted ciphertext is considered sensitive. So there's quite a few attacks and quite a few countermeasures that have been proposed. So the first attack was back in 2002 and perhaps even earlier, where the timing, there was a timing leak due to the fact that when padding check failed, the MAC was not computed. And the countermeasure in this case was to actually always compute both, with the caveat that when the padding check failed, you didn't actually know how much of the message was payload, and so you didn't know what to compute the MAC on, so you just assumed zero length padding, which actually still allowed some timing to leak through. That was later exploited in 2013, the Lucky 13 attack, which then said, well, encouraged people to say, make sure that when you implement this decryption, the number of compression function queries that are made during the MAC computation is independent from the padding length or from its validity. After that Lucky 13 attack, it was the countermeasures actually went further. Many implementations actually switched to a constant time programming policy where they forbade secret dependent branching and secret dependent memory accesses. On the other hand, some implementations went another way and tried to do some limited mitigation, but also hide whatever leakage was left behind some random delay in the error messaging. And that's the way Amazon Web Services Labs decided to go for S2N. We all know how that went. So very recently, Albrecht and Patterson showed that that randomization was actually insufficient. You could still extract information from the timing. And as a response to that, more mitigation was added to S2N, and the amount of noise increased, and it was actually increased even further recently. So the problem is that we exploited is that the additional mitigation was meant to better balance the number of compression function calls. In particular, when you're doing the hash finalize call for the inner hash, for the one on top, this is a diagram of HMAC. Depending on the length of the actual payload, that finalize call may actually make 1 or 2 compression queries. And essentially, if you have enough space in your buffer at the end to have 9 bytes, then you're going to be making only 1 call. If you don't, then you're making 2 calls. The problem with S2N, the S2N implementation, is that it was checking for 8 bytes only. So in some cases, it was making 1 too many compression function call. And that led to large timing discrepancies for some interesting values of the payload length that could actually be exploited to recover plain text in the same way that the Lucky 13 leak was exploitable. This was not taking into account the randomized delay at all. So for a full S2N deployment, there was no way to exploit this. But if you were picking and choosing the parts of S2N that you were using, or if you were using self-serve blinding in particular, so you could actually ignore the fact that there was some waiting going on before messaging the other side, then you would be vulnerable to this. You would be vulnerable to this despite the fact that S2N is written and comes with an extensive set of test cases, some of which were actually designed to test exactly this timing behavior and making sure that it was not secret dependent. So this is a property that's eminently not testable easily. And so this is why we want to go for proofs of these properties and proofs directly on the implementation. So to obtain those proofs, again, this is going to be a very difficult problem. You're looking at an x86 implementation, you're extending the semantics of that language, the assembly language, with some specification of its timing behavior, and you're trying to do a security proof on that. And so the way we're looking at it is to actually cut the problem into 3 subtasks that are, in isolation, fairly standard and actually allow you to obtain the result you want. So the first task is obtain a black box, proof of black box specification security. So on a fairly high-level specification of the scheme, obtain just a standard security proof. And then once you have that specification, you come up with your implementation or you take it off the shelf, and then you prove functional correctness of that implementation with respect to that spec. So you prove that the input-output behavior of the implementation you have is the same as that of the specification. And here, overall, that functional correctness needs to talk about the final x86 implementation. And then finally, once you have both of those things, you can start considering leakage simulation, which is something that you have to prove on the x86 implementation. So it's not something that relates to objects. And what you're proving on this is that for all inputs, the leakage produced by the execution of the algorithm can be efficiently and perfectly simulated, given only public inputs to the algorithm. And from those 3 things, 3 components, you can actually prove side channel implementation security. So in order to specify better what those 3 properties are, I'll be diving directly into the MEECBC example. So in blue are the things we prove, and in red are the things we deduce from that. So the first thing we do is write a specification of MEECBC in EasyCrypt and formalize a proof of its security directly in EasyCrypt as well. Then we write a C implementation, which is this object here, sorry, and prove that it's equivalent to its EasyCrypt specification, instantiated with particular block lengths and a particular padding function that fulfill all the other requirements that are premises to this security theorem. And from just this compilation, we get immediately that if you compile this C implementation correctly, you'll be getting something that is black box secure, that has the same black box security properties as the algorithm it implements. Going further, once you come up with an AES implementation and an HMAC SHA-256 implementation, which are the two components we decided to go for, and you compile that further. So here we're using CompCert, which actually comes with a proof of semantic preservation. Then you obtain some x86 code that, again, you know is black box implementation secure. And then you do a leakage simulation proof on this. And for that, we also use an off-the-shelf type system that actually checks leakage simulation. And then you get your final result, which is side channel implementation security. So I'll be going briefly through all of those steps, and in particular, detailing the security definitions. So starting from the left, we had a black box specification, security. So here, I'll only talk about the secrecy property. So it's in $CPA, which is an indistinguishability. So yeah, let me start again with that. It's in $CPA. So the security game says that the adversary is trying to distinguish between the real system, so something that encrypts a message using the encryption algorithm, and another ideal system that just samples the ciphertext at random. There's a +1 here for the IV. There is a slight tweak with respect to standard notions of $CPA, in that we actually add a dummy decryption oracle here that you wouldn't see in standard textbook definitions. And all it does is call the decryption oracle and then ignores its result. It'll become clear why we do that on the next slide. In addition, in the EasyCrypt part of the proof, we also prove some weak form of length hiding, where we actually say that the padding function that we use allows for some hiding of this length. So here, the ciphertext will not be exactly the length of the plaintext +1, but some other function of it. But we don't actually transfer that to the implementation, because usual implementations of the encryption algorithm, for example, do not actually hide the length of the plaintext. So this is what we prove on the specification. What we want to prove on the final implementation is security in this setting. So you have a machine, so you have a language, which is not shown here, and a machine M that implements its semantic, that animates its semantic, so that does step by step what the program should be doing. And along the way, it also produces some leakage trace. So here it would collect, for example, whatever leakage is caused by the execution of an instruction, and appends it to this L variable that's output at the end. And we're considering here implementations of the encryption scheme, so here pi star, and I'll denote with star anything that's an implementation. In our final theorem statement, we'll be using the machine M that's been used previously in particular in the type system we use for leakage simulation at the end. And so the language L is x86 assembly. Its semantics are those that are formalized in CompCert, so in that certified compiler I was talking about. And the leakage traces are constructed in a way that essentially they reveal the ordered sequence of the branching operations taken during the execution, and the memory access is done during the execution. So essentially matching that constant time programming policy. And so here you can actually see now why we had this dummy decryption oracle here, in that here we're actually, this is no longer a no-op. So when the adversary makes a decryption query in this implementation model, he doesn't get any information about the decrypted plain text, whether or not it failed or anything, but it gets the leakage trace that has been produced. So that matches the scenario you would be in when you're mounting a side channel attack. You might not get anything because, well, the program is going to fail anyway and not tell you why it failed or how it failed. But you might get some information from the time it took to tell you I failed. Otherwise, other than this, it's a straightforward modification of the previous definition. So whenever you had, you were getting a result from the specification of an algorithm, now you're getting a result from its execution by that machine, and along the way also producing the leakage trace. Leakage traces are treated as public data, so you're always also giving them to the adversary in particular. Here in the oracles, you're also returning them to the adversary. So how do we go from obtaining a result in this setting to obtaining a result in this setting? Well, as I said, we're going to be additionally, in addition to black box specification security, also proving two other properties. The first one is functional correctness. So functional correctness, you can express it as a game, although it's not the standard way of expressing it. And here, the game would be parameterized by the machine M, a specification pi of the primitive or the protocol, and an implementation pi star. And the adversary is given access to an algorithm eval. Essentially, you can make queries to this eval algorithm. K is just used to decide which of gen, enc, and dec the adversary tries to execute. I is inputs, and R is randomness, so randomness inputs to the algorithms. And essentially, that eval algorithm is going to execute both the specification and the implementation on the same inputs and randomness, and just set a bad flag to true if they return different results. So essentially, at the end of the execution, if the adversary has managed to make the implementation and the specification return different results, then he wins. And we'll say we want total functional correctness when we say the probability of returning not bad is 1. So the adversary has no way of ever causing such a divergence in the behavior of the spec and its implementation. So this captures perfect correctness rather than probabilistic. So if you prove this, you get a very strong result about the implementation. So in particular, it would prevent algorithm substitution attacks if you can actually check it before running the program. So if you have, at runtime, some guarantees about what is actually implemented and how it's going to be run. If you know that your spec actually is secure also against algorithm substitution attacks, then you might actually be able to weaken this requirement and allow some probability of the adversary managing to cause a discrepancy in the behaviors. The important part about this definition, though, is that even though we expressed it as a game, it's actually trivially implied by standard notions of correctness in program verification or in programming languages. So it's either just called functional correctness, or if you lift it to the compiler that produces that implementation pi star, it becomes semantic preservation. So in particular, CompCert, equipped with its proof of semantic preservation, tells you that for all specification pi, so here the specification would be a C program, it produces an implementation in assembly, pi star, that fulfills this property. The third component that we needed in order to finish the proof is leakage simulation. And leakage simulation is essentially the same as the total functional correctness, except it talks about the leakage instead of talking about the output. And it's all, instead of being parameterized by a spec and an implementation, it's parameterized by an implementation and a simulator sigma here. And so the game is essentially the same. So the adversary is given access to this leak oracle, and this leak oracle allows the adversary to select an algorithm that he wants to run, and some input and some randomness input to this algorithm. And the leak oracle is going to execute the implementation and extract its leakage trace L, and then execute the simulator on some projection of the inputs and extract some leakage trace L prime. And the adversary wins if along the way he manages to make a call to leak that yields different L and L prime. So here, this projection of the inputs is essentially decided by what is considered a public input. So in this setting, it's actually completely determined by the security game that we had, so in $CPA. So in this case, the key generation algorithm has no input, so its public inputs are the empty set. The encryption algorithm took as input a key, a message, and some randomness, and the leakage that the public properties of those inputs that we're going to allow the adversary to know or to guess are the length of the key and the length of the message. And in the decryption algorithm, the public inputs are again the length of the key and the whole ciphertext. That's completely controlled by the adversary. So essentially, if you look again at the in $CPA security definition, the adversary is given access to this real or random oracle. And here, the only thing that is common to both of these, well, would be the length of the plain text, which is used in both, and the length of the key, which is not used in the second one, but is revealed anyway, well, is known publicly. And same thing here in the decryption oracle. The ciphertext is controlled by the adversary, so it's public, and the length of the key is also known. Again, the important aspect of this definition is that it corresponds exactly to some standard security notions used in language-based security, and in this case, non-interference, which says that if you have a program, a set of public inputs, and a set of public outputs, here just the leakage trace, that program is non-interferent with respect to those two sets. If for all pairs of input values that are equal on their public part, execution yields public outputs that are equal. And whatever happens on the secret secret inputs and outputs. And that property is actually easily and efficiently verified using type systems and other techniques. So here again, we have a property that can be very easily verified on programs. In addition, we can actually weaken this by allowing the simulator to use public outputs in order to simulate the leakage trace. And we retain our top-level result that says that if you prove black box security, functional correctness, and leakage simulation in this weakened form, then you get implementation security as well. So this would, for example, allow you to branch on some secret-dependent value that is anyway revealed by the output of the oracle. So going back to this application, to MECBC. So here, we just prove the standard notion of security on a standard description of the construction. This functional correctness result from specification to the C implementation we obtain using Framacy. So we extract from the EasyCrypt spec a specification that's used in Framacy, and we prove equivalence between the two using that verification tool. So that gives us only black box implementation security on the C program. But it also allows us to transfer the assumption. So here in EasyCrypt, we had some abstract PRP and some abstract Mach function. And we had assumptions on them that yielded these two security properties that we want on MECBC. And because they remain abstract at this level and we can't actually prove anything about them, we keep them abstract here. But when we move to the C program, we actually turn these assumptions into assumptions on the C implementation of the primitives that we choose. So here, the assumption from P is a PRP gets turned into that C implementation of AES-128 is a PRP in the implementation model for that language. And same thing for the Mach function. If you wanted to go further and actually verify the implementations here, you could return back to AES-128 is a PRP as some abstract algorithm, but there is very little value in doing that. Yes. So all this comes at a performance cost, but it's actually very minor. Well, very minor with some caveats. So this table shows the time taken to decrypt a 1.5 kilobyte TLS record. And a very large part of that cost is actually due to constant time AES. So if you look, MECBC x86 is the only one that is the one that was produced by that entire process that I just described. And it is a lot slower than OpenSSL or S2N. And the main difference, all the other ones are actually not that bad. Well, especially this one, where we use a hardware implementation of AES. It's not that bad compared to the other two implementations. And it's still compiled using Concert. When we actually profile this implementation, or these two, 97% of the time is actually spent in the constant time AES implementation. So a large part of the cost is due to the constant time AES. Some of that is actually due to Concert as well. Typically, Concert introduces a 2 times performance factor. And we kind of match this if we compare with something that doesn't use constant time AES, the slow constant time AES. And then a small part of that is due to the implementation of the construction itself that we do in constant time. And since we use the same countermeasures as the OpenSSL implementation, you can actually see what cost this incurs. And this is a very small part. So a quick summary, if I have the time. So some formal guarantees can be obtained in realistic settings, in particular on implementations and taking into account some side channels. We propose a framework that allows you to do this by breaking down the problem into smaller subtasks. But it still incurs a cost, both in terms of proof effort, and in practice, most of the effort is spent formalizing the security proof and formalizing the functional correctness proof. And it's also worth noting that when you twist the implementation to make it constant time, you actually make it harder to verify functional correctness. So a lot of the time was spent trying to undo in the proof those constant time countermeasures. And there's also a cost in terms of performance that in practice mostly comes from primitive design. And in theory, most of what's left could actually be absorbed by the proof effort. So if you discard Concert and try to do a functional correctness proof directly on the final assembly code, then you might actually absorb some of that performance cost. And I'll leave you with some advantages of our method. And that's it. Thank you.